Okay, part two of the products and management for timber. Um, this is one of our master tree grower courses some time back. I've lost a bit of hair since then, and where we work with farmers to help them understand the basic principles of how trees grow. Having shown them the market, we start looking at how we can manipulate our trees to suit the market requirements for different products, whatever they're interested in growing. The measurement side, we talked to them about how to measure tree diameter. Diameter is fundamental, as we saw in the products, to the quality and therefore the price of different logs. So there is a convention in Australia and around the world to measure diameter at about 1.3 meters above the ground. That's the old 4-foot height. And at 1.3 meters above the ground, we wrap a tape around the tree and measure diameter at that point. So we all tend to agree. When the log's on the ground, you can clearly measure the diameter at the small end and the large end, which may be important for marketing. But what we're focused here on is how we can manage the trees standing. So we need to understand how our diameter growth is going in terms of tree growth and health, and how we can therefore manipulate it to grow larger diameter if that's what we require for the market. Market diameter is measured, we use a tape, probably got one lying around here in the office. It's our master tree grower tape, and this tape is wrapped around the tree. The important point is on the yellow side of the tape, it's just a normal metric ruler, but on the white side, it's actually a diameter tape. And that means it calculates the effective diameter of the tree if you wrap it around. Now, here's a Kenyan village chief. I gave him a tape to measure his Australian silky oak trees. These were initially planted along boundary plantings to demarcate the edge of the plot. Historically, when the land was used for food crop production alone, they used to use a lily, I think, that grew naturally in the area and it was easy to transplant. And they would plant that along the boundary so that the neighbours could agree on where the boundary line was. And when they started growing trees, particularly coffee and some fodder trees and fruit trees more, they needed something taller that could demarcate the boundary. And an Australian government program had been exploring silky oak along with other species for firewood production and other products. And they found that they were also easy to transplant. So the villagers planted them along the boundary. Subsequently, they cut the lower branches off to reduce shade or to get fuel wood or provide fodder. And they ended up with some really nice prune trees. And then when in Kenya they banned the logging of native forest, there suddenly became a market for this timber. And buyers were going onto these small farms and offering small amounts of money for their trees. Some villagers sold their trees, others said the price wasn't right, but they had trouble negotiating because they didn't have an understanding of volume. So when I gave this tape, the landholders were excited that they could start using an objective measurement of diameter as a guide to how they could negotiate a market price. So you wrap the tape around the tree, 1.3 meters above the ground. That would measure normally the circumference, but this tape actually measures the diameter because it has circumference equals pi times the diameter. So if on the tape, on the white side of the tape, as I was showing you, the distance between those numbers on the white side are actually pi, 3.142 centimeters. So the number of those around the tree will give you a measure of diameter. It's much more effective than trying to measure it with a caliper and much simpler. Now, basal area, which you need to measure the volume of a tree, is the cross-sectional area of the tree at that height. So you should all know that that's r squared times pi. So in order to use the diameter measurement we had, which was in centimeters, convert it to radius in meters, because we need a measure in meter squared up here. We divide by 200, square it by pi, and we get a basal area measurement. Now the basal area measurement is really useful for a couple of things, not only for volume calculations, but more particularly for understanding competition in a forest. So I need you to understand that terminology, because I'm going to use that in when we look at how much basal area there is in a whole forest, not just the number of trees and how large they are in that area. Tree height. Tree height's a good measure of early growth. It clearly relates to the volume of the forest. You double the height of the tree, you'll essentially double the volume for the same diameter. But in most circumstances, it doesn't have to be very accurately measured, since when you cut a tree down and take a log out, it doesn't really matter how tall the tree was. But you can get a good volume measurement. This is the technique we teach our master tree growers to use, that involves the master tree grower tape, measuring the height, determining what 10% of the total tree height is, then measuring that height there and multiplying by 10. You can read about that technique in the Farmer's Forest book, on the chapter on tree measurement, if you're interested in using a simple height measurement. It's much cheaper than the syntoclinometers or laser beams that professional foresters would use. We really can't afford those in a farming environment. The final factor that's really important for management is understanding the form of the trees. Now, form really depends on the quality of it. In terms of form, depends on the market. But essentially, I judge trees as having either form 1, form 2, form 3. Now, form 1 is a perfect tree for the intended use. Now, this could be extremely straight, barrel straight, if you're trying to grow telegraph poles, for example, or it could be almost straight if you're trying to get short sawlogs or furniture grade timber from a high value tree like a blackwood. There are other trees that, for some reason, whether it's form, disease, branch damage or something like that, which I call form 3, which will never, even over time, grow into something useful for sale. And then you've got trees in between. Now, clearly, if you're trying to improve the quality of your forest, you want more form 1 trees and no form 3 trees. On our farm, we only leave a form 3 tree that would never be good for the market if it's providing some other services, biodiversity, shelter, some sort of reason why I'd want to keep a tree there. Otherwise, it's using up resources that could go to the growth of form 1 and form 2 trees, which ultimately could produce a higher value product. Calculations of volume, I'm just going to put these formulas here. So you can, once you've got the basal area of a tree, based on the diameter measurement, the height, you can assume a tree is a cone shape, which is a nice conservative estimate, because most trees are actually more like a missile than a cone. So they tend to have more volume than a cone would estimate. And so that's good to be on the conservative side when your measurements aren't entirely accurate. Like a height measurement might only be within a meter or so. And the other point about about doing a simple measurement of volume is that if you use the same assumptions over a period of time, you can get a measure of change, which is more accurate, even though it might reflect the real precise measurement of the tree. So there's a formula for the cone. So if our trees are, we use that diameter measurement again, convert it to radius, square it in meters, by pi, by height divided by 3 will give us a measurement. So let's assume we've got a tree 40 centimeters in diameter, 25 meters tall. We can calculate the basal area at 0.12 meters squared, and then we get basal area times height divided by 3. That is 1 cubic meter of wood in its total height and diameter. So if you want a cubic meter of firewood, for example, that's the sort of tree you'd be after. Log volume is a little bit simpler. We tend to disregard all the branches in the upper part of the tree, and we get a diameter measurement and a height measurement just for the log. And we may measure also the taper, the degree to which diameter drops as you go up. You could do that and come up with a more accurate measurement of the diameter of the tree. Taper may be in the order of 1 centimeter reduction in diameter for every meter going up, although there will tend to be some swelling at the base, but that's mostly lost in the stump. So you've got here a possibility of using a mid diameter if you can climb up there, or you can And this is what a lot of log traders do around the world. They reach up and they try to get a mid diameter to calculate that and try to avoid the larger diameter at the base. And clearly a farmer would like the measurement down here, and the buyer would like it way up here. And clearly, as long as they both agree on the price and the method, it doesn't really matter. So that gives you an example of calculating a cubic meter log. If you want to think about it, if you had a chance to walk around our farm, we've got a lot of trees in the order of 55 centimeters diameter at the base, at breast height, 1.3 meters, and they're pruned up to the order of 6 meters, which is the height I've calculated here. That, to me, that's a cubic meter of log, and it's a good size as well for start milling timber. You get 75 centimeter diameter, and suddenly the volume of that log will double into the order of almost 2 cubic meters, and that's because you increase the diameter a little, you have a significant effect on volume because you're squaring that relationship here when you square the radius of the tree. How much carbon? Rod will talk more about this, but you can use any volume estimate of a tree to look at the wood density and try to account for above and below ground branches and roots if they're relevant to your market, and you can work out the total biomass, and then from that take a carbon estimate, carbon calculation. Let's take that 1 cubic meter log or 1 cubic meter tree. Some of our faster growing eucalypts, the wood density might be about 0.55 tonnes of dry biomass per cubic metre. That would represent, in terms of carbon content alone, about half of that is in carbon, between 49 and 51%, but we can pretty much assume half of it is the carbon element. We multiply by 3.67 because that is the amount of CO2 required to have that amount of carbon in it, and that will take us up to about 1 tonne of CO2 equivalent. So I've roughly put these in to show that a cubic metre of wood from an average eucalypt, even a light eucalypt, will have a tonne of carbon dioxide equivalent in it. So if you have a denser wood like an ironbark or a tallow wood, you're going to get more than that. If you have a lighter one like pine, which when you dry it out might have 0.45 tonnes of dried biomass per cubic metre, you'll have slightly less. But roughly speaking, if you want to see what a tonne of carbon looks like, it's basically a tonne of CO2 equivalent. It's pretty much a tree of that size, 40 centimetre tall tree. Forest basal area. I mentioned, and this is important for understanding where I'm going to get to with how the forest grows. The forest basal area is just the basal area of all the trees in the forest per hectare of land. So we measure a plot of trees and calculate the basal area. Then we expand that plot if it's representative across a hectare, and we can get the basal area in square meters per hectare. I'm going to show you some graphs that actually use this as a measure. It's great because it not only accounts for how many trees there are on that land, but also how big those trees are. And that's both the number of trees and how big they are, which affect how much competition there is on that forest, but also the volume, because basal area, as it's related to the volume of a tree, also relates to the volume of the forest. We have a technique using this master tree grower tape again that can be used to measure basal area. It involves holding the tape at a certain angle to a certain distance and counting the number of trees that appear bigger than the tape. I won't go into the detail, but it means I can go into the forest like this and I can calculate pretty closely the basal area of that forest without actually measuring a single tree, the diameter of a single tree. It's a fantastic technique developed by a forester in Germany over 100 years ago, and it's used in a number of different tools such as perspex wedges that split the light, or a simple technique like I've shown you with the tape. And if you want to use that, look it up on our Master Tree Grower site or in the Farmer's Forest, and you can see how to measure trees. So they're the fundamentals that we need to start exploring the principles of silviculture, how you can manipulate the forest as it grows to direct growth in the way you want to take it. I keep saying it doesn't matter if your goal is biodiversity, firewood, seed production, it's all the same. if we understand the growth and the dynamics of a forest, then we can direct growth the way we want to take it. I'm going to use wood production as an example, particularly focused on the growing of sawlogs, which may be appropriate for smaller growers, but those principles apply whether it's whatever your product, whatever your value. And that comes from understanding the basics of tree growth. Above ground, and let's ignore the root system for a moment, above ground height occurs in two ways. The trees get taller from the tip and their branches get longer. This height growth and branch extension is a result of meristem division that occurs at the growing tip. Now, unlike bamboo, which grows out of the ground and then elongates and pushes up, so if you put a tape, put a mark on a bamboo stem, it will actually move up over time. If you put a nail in a tree, it doesn't move up ever. It stays exactly at the same height because all the growth is occurring on top. So it's like adding new cells to the top in a way that we start each during the growing season, new cells are added there. Those new cells also, as they're added, elongate a little bit. So you do get this extension pushing up that growing tip just below, but this only occurs near the leading shoot and not like bamboo, which occurs right across the whole stem. So this might be the growing tip, that the top 3 or 4 centimeters of the tree, which is actually adding new cells and elongating those cells as it grows. So if we want the tree to grow taller, or we want the branches to go longer, or anything to do with elongation, we're talking about the growing environment around this tip and its supply of nutrients in order to grow, sugars particularly, in order to extend. There are different types of height growth. I won't go into the determinate and indeterminate in detail, other than to say that some plants already determine how tall they're going to grow before they start growing. The number of cells that they could add is already defined in some way, and that might apply more to northern hemisphere species in the colder environments, and such as the black walnut and the oaks. And indeterminate growth, they can keep growing high as long as the conditions are appropriate, and that's more common in the tropics and in our environment. Height growth, how can we see it in a log? It actually occurs right up the center of the tree, because that was the original growing tip, and then subsequently all the wood around that is actually laid down in the second part of the growth. But height growth does not produce wood in the way that we understand it. It's usually a corky material. We call it the pith. It's rarely seen as a positive in any furniture or high quality product. It's suffice to say it's not wood in the way we see it. It's a pith that runs up the stem. So this is the trace left behind by that growing tip. It could only be a few cells wide. In some cases like pine and teak, you can see it might be 3 or 4 millimeters wide. In eucalypts, you can't even see it. It's just that point in the center where there was height growth. And I call it a corky, non-woody material running up the center of the tree and up the middle of all the branches. What tends to happen in a piece of wood, it shrinks around that and tends to crack, particularly in the hardwood species. Factors that determine how tall a tree grows, how quickly it grows in height, are many. It's really to do with humidity around the growing tip, water supply from the roots, how fertile the soil is, what insect disease, and how exposed that growing tip is to the environment, which really reflects this humidity around the growing tip. There are some species that, as I said, are determinate in height growth. It's already defined by how well the season was the previous year and how many cells were laid down. And some species like teak, as soon as they start flowering, they stop really grow. Their height growth falls dramatically as the focus goes into flowering. But the juvenile phase, you'll actually find it differently. So this is less mature teak. You can see very strong height growth occurring here. A single stem getting taller and taller. When these teak trees reach flowering age, that height growth extension will be reduced dramatically. So how can we actually get better height growth? Focus on deep fertile soils with a good water supply, irrigate the trees, particularly to extend the growing season. What tends to happen with height growth, it occurs in spring in the temperate areas and will continue until water becomes a limiting factor. So if you have a dry spring, height growth will stop early, and then there won't be much height growth for the rest of the year. Whereas in a good spring will have height growth and elongation of stems right up till Christmas. And I'm referring to sort of oak trees. Shelter the plants from wind, and you can achieve that by planting in a sheltered location, putting windbreaks around it, or having the trees very close together so they shelter each other. I call that mutual shelter, and that's pretty fundamental to getting good height growth and form on an exposed site. If these factors are limiting, disease and fertilizer and other factors, well, if you eliminate the limiting factor, you'll actually get better height growth. Stem growth is the wood that forms around that pith. So here we've got a piece of teak. Every year it puts a growth ring on and gets larger in diameter. I hope you understand that the wood laid down when the tree is young is in the center of the tree, and the wood laid down just below the bark. More recently, when the tree is older, is just below the bark, is out here. So when I was talking about juvenile wood, it tends to be the wood in the core that is laid down when the tree is young that has those low density characteristics of juvenile wood. And as we move out here, wood density tends to increase because the tree is larger, the growing tip is, and the photosynthetic leaves are further away. So by the time the sugars flow down the cambium, which is this, flow down to the cambium through the phloem here below the bark, the concentration of sugars and hormones aren't as great, and you get a better quality wood formation being formed. So all growth occurs at that point. The cambium, which is the only growing part on the stem, is just below the bark. Very thin layer, a few cells wide, and it produces wood on the one side and bark on the other. So this little strip of wood just underneath, a little strip of cells underneath the bark, is where we're focused. If we want to grow diameter, it's about the supply of sugars and the health of this cambium layer, and it'll produce bark and produce wood. In the many species that hold their bark, you can see growth rings in the bark as well. So the bark on the outside is actually the bark that was laid down when the tree was young, if it's retained, and the new bark is formed on the inside here, the opposite of the wood on the inside. The reason the bark cracks and fissures develop, the channels develop in the bark of trees that retain their bark, is because as the tree gets larger in diameter, the bark that was formed when the tree was younger wasn't suffice to cover the whole tree when it gets larger, so it has to crack. The cracks are actually filled up with secondary growth, corky material, and that's where we actually get cork from, a tree an oak tree that produces a lot of corky material to fill in those cracks and provide secondary bark. So here's the summary. We've got a pith in the middle, we've got heartwood and sapwood. As I said before, sapwood's an area where water travels up the tree. Heartwood is wood that used to be sapwood, that now that has chemicals deposited in it. It has no active role in the living part of the tree. There's no live cells there. Its role is simply to hold the leaf up. The sapwood is around that, same cell structure as the heartwood, but open cells that allow water to travel up, and also where the tree can store a lot of carbohydrates and sugar during the off season. And the sugars come from photosynthesis. They're fed down the inner bark, or the phloem from your old biology class, and then moved into the sapwood or taken back across here by the ray cells I discussed. So all those elements we talked about in the previous lecture are all there in part of that wood formation. This is the biology of them, and this is what we need to understand if we want to grow that product. So what happens when you ring bark a tree? I find this is useful for farmers to understand. I often pull my knife out, saw out, and cut the bark off a tree. I cut a little bit deep here with a chainsaw, but essentially the sugars that flow down the tree can only reach this point, and they can't flow down because you've taken off the bark. The wood is still there, so the water still travels up the tree. So what happens to the canopy? It's still getting water and nutrients from the root system. It's sending sugars down. The canopy itself doesn't even know the tree's been ring barked until the root system down here is so starved of sugars that it dies and the water and nutrients stop going up. And that's how ring barking kills trees. It takes a period of time. Had a few farmers ring me up and said, I've ring barked my trees, but they won't die. And that must be because the root system is being maintained by sugars from another tree through root grafting. So you can have a living canopy, a living root, and no connection between them on the tree, because or no connection of sugars. The waters can still go up, but the sugars can't come down. The other thing you find is the diameter of the tree tends to be greater, or keep growing above this, where there's a high concentration of sugars. So you get a fatter tree above the cut than below if it takes a year or so for the tree to die. That's sort of, you see that in terms of live stumps. This is a tree I cut down many years ago when it was probably only about 40 centimeters in diameter. And over the last subsequent 15 years, it's been growing still in diameter despite not having any leaf on it. And that's because it is root grafted to its neighboring tree. And this root system of this stump is actually feeding this tree over here now. So stem growth down here is driven by all the sugars that come down from the leaf area above it. And this is important because we know that if we prune the tree, we reduce the leaf area, and that reduces the flow of sugars down the tree, and that will temporarily slow diameter growth. If we give this canopy more space, more light, it will produce more leaf and more sugars, and that will drive diameter growth. So a lot of what we're going to talk about with regard to thinning and spacing and pruning trees is actually about manipulating the canopy. Some of it will reduce growth temporarily in a positive way, actually. But as we give the tree space, have a large canopy, we get much larger diameter growth. To illustrate that to a group of farmers up in Darwin, this is in a teak plantation near Darwin. Now, teak's a great tree to look at silviculturally for two reasons. First of all, it's deciduous, so that we know that every growth ring we see in a sample is 1 year's growth, and because it goes in a dormant dry season. The same thing can be done in oaks. In eucalypts and other evergreens in the tropics, each growth ring, you could have 2 or 3 growth rings in a year, so it's very hard to determine the age of trees. But in the temperate regions, or using deciduous trees in the tropics, you can. So I got the farmer here to cut down a tree. This is, I think, a 13-year-old teak plantation. You can see it's quite closely spaced. The trees have grown well, and I'm looking at those trees saying they're not going to reach their potential because there's too many trees. So I need a method to convince the landholders that if they have a teak plantation like this, they've got to cut half the trees down in order to get give the retaining trees enough light. So I got the landholder to cut one tree down, and we removed this sample from that tree. You can see it has all the characteristics. You can see the pith, the heartwood, and incidentally, you can see how the heartwood is not following a growth ring. It's just an area of staining caused by the filling up of the cells with those chemicals. And then we have the sapwood here, which is open and white because it transports the water up the tree. We have the cambium, which you can't see, but we know where it is. And we've got the inner and outer bark down here, which is where the sugars are flowing down. Now, what you can see is the growth rings, and that's because it's a deciduous tree, and we can see that each one of those rings, so we can go right back to when the tree was planted. Let's assume it was planted when it was this size. We have our first growth ring, second, third, fourth, fifth, sixth, and you can see how the growth rings in those early years varied. There was a very big year's growth, and then little, and then not a bad one, and this sort of growth here, up and down growth, really reflects the growing season, whether there was a cyclone that blew the leaves off so you didn't get more growth, or insect attack or leaf. This was probably a good season, this was a good season, this was an average one, and the growth continued in that way. But as we go out, you can see the growth rings get closer and closer together, and that growth isn't as varied. Out here we got about 1 centimeters increase in diameter between the growth rings, 2 if you count the whole diameter of the tree. Out here we're talking millimeters. And what I needed was evidence to argue that that slowing of growth is due to competition between the trees for light. So let's look at the data. This is the diameter of that sample. This is the age. You can see this is the annual growth. It grew up to 2 centimeters diameter per year, but then slowly declined in growth. So it's only a few millimeters per year. And this shows the total diameter of the tree. The way that it's gradually getting less and less and less over a period of time shows that the seasonal variability had less to do with it. And it was actually the increasing competition. The trees got a little bigger, And because they all got a little bigger, they all competed a little bit more for light, and to a lesser extent nutrients and water. But I'm going to argue that it's clearly light is the bigging factor. So what's slowing diameter growth? Well, let's look at a couple of teak samples. I went to the teak research station in northern Thailand, and some of you might be able to read that. I've covered up the age of the tree. From what I've told you about tree growth, I want you to pick which of these two samples that come from the same forest area, but are totally different in the way that they're managed. These two samples have been collected because they're both producing about the same size of teak heartwood. There is no market for teak sapwood. It'll rot off quite readily. It is the heartwood and the colour of the heartwood and the quality of the heartwood which governs. So these two samples are similar, but this one is fatter because it has a much wider sapwood band. A much wider sapwood band means that you've got a canopy that needs more water. A larger canopy on the same site was leading to better growth. So you've got faster diameter growth here. Slower diameter growth tend to be a reflection of a small canopy, which requires only a small water pipe up here. So the tree has, rather than maintain a big water pipe, has actually laid down more heartwood. And as a result, so I'm going to show you that this tree here is 63 years old. This one here is 25 years old. So in terms of management, the only difference is that this plantation here, the trees were thinned to concentrate growth and light and therefore growth onto the best trees. And as a result of that, they grew a hell of a lot faster than they did over here. So there is I've to put in some data here for teak plantations or different plantations around the world, looking at how many trees there are and how large the average diameter of the forest is. And you can see a trend here. If you have less trees per hectare, you can have larger trees. The important point I want to add is that if you want to grow 50 centimetre diameter trees, you're not going to get 1,000 of them per hectare. This line represents the limit of the species, if you like. Now, there are some data points up here, and I know it can extend 200 trees and stuff, but this was from one publication where I got diameter growth from a range of different species. I've just got to work out where my batteries are. Okay, laptop's plugged in. If we want to grow 55 centimetre diameter trees from the data, and as I said, I've got some data points up here, we're looking at less than 200 trees per hectare in order to give them space. And this is what it might look like. This is a teak forest that's been pruned and thinned over about 70 years. It's actually in southern India, in Kerala. And I was taken to this because it received what might be called high quality colonial forest management before independence in the early years. And you can see the sort of spacing between the trees that will give you this larger diameter growth of teak. Now, teak is a species that loves light and doesn't grow well in the shade, so it needs space in order to maintain large diameter of trees. So essentially what we're dealing with, planting a whole bunch of trees when they're young, letting them grow well in their own shelter, and then from those we can pick the best trees, and more light is available to these canopies, so they'll grow faster, and we can do the same again, and over a period of years we'll thin down to a lower stocking of the best quality trees, and they'll have the largest diameter growth. They'll still have good height growth because they had the shelter from each other, but as they grow they need less shelter because the trees around them are less trees to get the same amount of shelter, and we can get larger diameter growth, and over time you can get those large fat logs. So that's sort of essentially the principles of thinning. And for different species, because of their shade tolerance, we can look at how much different light levels they actually need in the forest. This is a teak regime coming from research in Costa Rica. What they're suggesting growers do if they're focused on just producing teak sawlogs. And here you can see when the trees are 0, young, small in diameter, you have about 1,000 trees or more per hectare. Let them grow to about 15 centimetres, and then you harvest half of them. Even if you can't get any product from that, it's worth cutting down half the trees, because these trees will then grow faster up to 25 centimeters, and then half again almost, and then you're progressively coming down to this small number of trees, around 100 to 120 trees that'll be average 50 centimeters in diameter. And because you've done the thinning earlier, before the competition becomes intense, you can get there much quicker than you do if you behave like a native forest and allow the trees to kill themselves over time. So this is sort of a line here. What that regime does is essentially follow a concept of maintaining a 20 square meters per hectare basal area over that full time. That's not a bad guide, but it's not also a very good one. It tends to result in too many trees when the forest is young, and not enough. Too many trees when they're that age, and not enough when they're this age. I would prefer to go here and actually have less trees when they're young, and that means you can get this faster growth but still have enough to choose from. Less trees means less pruning work, so we can reduce the pruning costs. For example, here at this size of 15 centimeters, I'm suggesting you come down and have less trees. So come across from here at 15, rather than 700 trees, come down to 400 trees. And at this age, rather than have 300 trees, have 250. And you actually, all of those less trees in the forest for the same size means a lot less work. When the trees are older, you can have more trees, because a lot of the basal area, a lot of the competition is actually just heartwood. And but it still is somewhere in the same ball figure of about 100 and 120 teak trees per hectare. So pruning and thinning. Some of the aims I've listed here: how to grow a good tree, provide sufficient trees to maintain good height growth. You need that mutual shelter. On an exposed site, the more trees you need. You can mix species to get the shelter, and then remove that secondary species if you've got a slower growing one you want to grow on. Retain enough trees to select the best form. If you've got a highly genetically diverse, or that you have form factors that influence form, such as wind and insects, you need many trees to choose from to get good ones. Have more Form 1 trees. The harder you do your culling, the better quality of your forest when you leave it. So you need enough trees for that. Reduce the number of trees required pruning without compromising final volume. If you're planting a lot of trees, you've got a lot of intensive pruning work, as we'll discuss a little bit later. Why prune trees that will subsequently just be cut out? I tend to want to minimize that by having just enough trees for mutual shelter and selection, but not too many that you're wasting a lot of time pruning trees that will subsequently take it out. And if you do that, you can focus growth very quickly on the best trees and get down to large diameter very quickly. Because as we saw in the market discussion, whether it's teak in Indonesia or eucalypt trees in Australia or anything, larger diameter, more heartwood, is high value. And these large clean logs, this is a farmer in Java, and these are his teak trees that he had growing around his food crops when he was a younger farmer. Now he's basically a teak grower, and he's got many more young teak trees that he's managing. So thinning works in all species. And this photograph that I showed you before, you can now read it from the knowledge I've given you. This is a pine log in Tasmania. So knowing that, you know that each of these growth rings is 1 year's growth. You can see that the growth was quite good in the early years, but then it slowed down to be only a few millimeters per year. Now, what I need to prove to you is that if the forest is thinned, growth rate can return to what it was before. And this log I've selected out because you can see after it was thinned and given a time for the trees to recover and grow more leaf, its growth rate after that was similar to what it was before competition came to play. So we know competition is a factor because the growth in diameter slows down evenly. And we know competition is a factor because we reduce competition by thinning, we got good growth again. In effect, those years of slow growth are years wasted. For a farmer who's waiting for their trees to grow, if they can maintain a diameter growth like this, they'll have a much larger log and a higher quality log, because these growth rings being close together then further apart doesn't affects the grain and maybe the structural integrity and quality of the timber. As I pointed out, there is really no difference in wood density between a pine that's growing fast and slow given the size of the tree. So all this out here is good quality pine wood, but you've missed out on getting something. All we're doing with this is mimicking and utilizing the natural processes of forests. There's no fertilization, there's no irrigation involved by promoting diameter growth through thinning. And that's simply because these trees, we're using the principles of native forest competition. To illustrate that, let's take a forest. This is a native forest of Eucalyptus delicatensis, alpine ash. We know it's an even age forest that comes up after a wildfire, such as this area here, which was logged and regenerated. We've got an even age forest developing. This could come up easily enough after a wildfire, similar to what we've had in recent years, where you get an even age forest develop. It could be 150 years or more for the trees to reach this point. Now, the important point is that when you get effective regeneration after a fire, you might have 1 million seedlings or 100,000 stems of 100,000 seedlings develop into trees of this height, 3 or 4 meters tall. But over a period of time, and quite naturally, the stocking rate drops. The trees kill each other through competition, so that 150 years later, you might only have 100 stems per hectare. This graph is real data, the dark part of the graph, where someone actually measured how many trees there were per hectare and how big they were. This just shows how many there were. So they went into a forest at age 10 years in a natural forest after regeneration, and they found at age 10 years there was 5,500 stems per hectare. Then every 10 years they went back and they measured it, and you can see even by age 20, more than half of those trees had died, 2,000, 30, another half, 40, another half, and then subsequently the natural competition in the forest led to a decline down to a few hundred trees from that 5,500. So this is natural selection effectively. The survivors of the trees that were able to be just above the height of the others and get access to the light, because light was the most important factor determining dominance in that forest environment. Let's take age out of the equation and just look at the diameter of the trees and how many there were. So in this case, we're down here at the young trees, less than 10 centimeters in diameter, 5,500. This is what 10 years old. And then what we've got here is the stocking rate drops very quickly. So for 20 centimeter average diameter, we've lost 4,000 trees. To get to 30 centimeters average diameter, we lose another 50% of them. And you can see 50 centimeter diameter trees, we're down to that 200 or 300 stems per hectare. Now this is what we call the self-thinning line. There's no intervention by people here. I get frustrated when everyone tells me every tree is sacred, we've got to save every tree. Well, nature kills the trees kill each other. Competition. For the tree to get larger, it needs more space, so its neighbors either compete with it or it beats them. So that it drops. Now this thinning line is really interesting, because if you put it on a log-log graph, it becomes a straight line. And if you're interested in that, please read that chapter on growing eucalypt sawlogs. It's fascinating how the biology of this can be put onto a log-log graph and straight lines, and we can do the relative competitiveness of different species based on that. But for this purpose, just to show that over time we have self-thinning in forests. The exact same thing happens if we plant a plantation. If you plant 1,000 trees per hectare of this species, it'll grow quite well until they reach about 25 centimeters in diameter, but then it'll reach the natural limit for that species, and it will then follow a self-thinning line itself. Trees will die in the plantations through competition. So all we're doing when we thin a forest, we're preempting and we're deciding which trees will survive the competition. We're preempting the period of competition which will slow growth of all trees down and stress the plantation, making it more susceptible to drought and insect attack. If we get in there early and thin, we can actually maintain diameter growth rates before they start slowing and produce eucalypts or any species large diameter. This tree, for example, on a farm is 18 years old. And to look at some of the data for eucalypt plantations, this is all the data sets that I could find around Australia for different eucalypt plantations. This is the average diameter of the trees. Some of these plantations were the same ones measured over time, and the age of them. You can see from this data set that there is a pattern there. I've added a little data set here for other trees. You can see how they're 60, 70, 80 centimeters in diameter, and they're only 20 years old. What's the difference between that data set, which seems to have this natural limit, and this data set, which seems to break the rules, and we've got growth rates much higher? These trees are pruned. And the reason I joke sometimes and say that pruning can make your trees grow faster. Well, I've already explained to you that if you reduce the canopy area, you slow the growth down. But ultimately, if you prune and then space your trees, and you can't space them widely without pruning because you'll affect wood quality by just promoting large branches. But if you space the trees out, then prune them. Pruning allows you to put the trees out a much wider spacing. And as a result of that, you can have the advantage of low stockings without the disadvantage of large branches that result. You end up with large paddock trees or parkland trees that are no good for timber production. All these forests here were pruned. So we've got 60 centimetre diameter trees in 20 years. This is my own forest, 65 centimetre diameter in 28 years. These are averages of groups of trees, and so we, not surprisingly, get some trees up to 80 centimetres or more as we're getting on this farm in 25 to 30 years. Eucalypts also and competition. This just shows one way to see competition is to look at the trees on the edge of the forest, which are large in diameter because they've got more canopy, advantage of all that light. You go into this forest, and this is a picture from inside this forest plantation here, and you can see there's very little leaf on the surviving trees. In fact, some of these trees have already started to succumb to competition. This just shows how competition affects the growth of all trees in the forest, not just the ones that will subsequently die. So if you want to get large diameter growth, you need a lot of canopy on the tree. To get a lot of canopy, you've got to space the trees out. Different trees can cope with different levels of competition. Conifers tend to be more shade tolerant, so you can have them a little bit close together. Oaks, eucalypts, teak, and sun-loving species like that, you need them further apart in order to maintain that diameter growth. The trees, effectively, if you're going to space them out widely, need to be pruned. Otherwise, all these branches will be down the stem here and you'll have nothing useful for timber production. So competition, the closer the trees get, to summarize, if you grow them close enough together that they shelter each other, your height growth will be good. But let's say here, these trees out here are stunted because of exposure. They've grown widely apart at low stocking rates. As we grow them closer together, you get to a point here where about 600 trees per hectare, you can double the number of trees and they don't grow any taller. So please don't write in your exam response, if you grow the trees close together, they force each other to the light. That's not right. It's actually the opposite. If you grow them widely apart, the exposure to the growing tip means it'll slow growth down because you've got drier air. This is in a dry land area, dry winds growing across here, and that dry wind will damage that height growth and slow it down. These trees, you grow them closer together, they don't grow any taller. So what we need is, when the trees are young like this, just enough trees to get good height growth, mutual shelter, but then we've got to start thinning them down over time to promote diameter growth. Here's another trial of spacing. They're 11.5-year-old trees grown at different stocking rates from planting, no thinning involved. 100 trees per hectare, the red line here. The trees were stunted, they were 25 meters tall. You grow them close together, or just 400 or 500 trees was just enough to get mutual shelter, and then you've added another 4 or 5 meters of growth. Doubling the number of trees did not make them grow taller. Diameter growth, though, was very different. Diameter growth of the trees that had plenty of light and space was in the order of 32 centimeters, and add any tree and diameter growth is less and less. So you've got trees down here at 1,000, which are about half the size of those at the wider spacing. So we're balancing two things here. We want diameter growth, but not at the cost of height and form. But you can see here, if you planted 400 or 500 trees, that would have been quite enough to get the height growth. And then we could have manipulated that growth over time and thinned down to get the diameter growth as well. And this is what it might look like. You've got widely spaced trees, pruned up, they're all straight because the bad ones have been thinned out, and you've actually got here very large logs. Now the top part is heavily branched. It really depends on your market whether you think you can get enough value out of the second half of the log to justify having the trees closer together to control branching habit. For sawlogs, I doubt that's the case. Uh, uh, if you're looking for prune quality sawlogs, because if you space them widely, you get faster growth down here where you got most of the value. In fact, 80% of the value of a prune tree will tend to be down here. If you're in the pine market for knotty timber, there is an argument to plant them closer and try to get a second log out of that. And that may be the case depending on whether you're able to sell that second log into a market somewhere. Eventually, this wider spacing, particularly with the hardwoods, the flowering trees, we're probably talking about parklands rather than plantations or forests. And forest basal area becomes the useful measure of that. So how hard to thin? This is a pulpwood plantation. Trees are grown very close together. It doesn't matter about stem size. You use industrial thinning operations. You maximize volume production. This is our forest at about at almost a similar age. The trees are much more widely spaced. You see the wider spacing allows for understory and grass, which could be a positive for many farmers or for conservation values. It does mean that trees have to be pruned because these branches would stay alive, whether these ones are dead. By pruning, we improve wood quality and we promote diameter growth rates. And there's a few graphs I've done, and I'll refer you to that chapter on growing eucalypt sawlogs rather than try to explain all these graphs. And there's a much better explanation in that to illustrate there is some data that goes behind guiding how we might manage a forest for different products, how hard we might thin at a certain diameter to get that. And then we've got to work out how the practical way of doing it. Thinning, we can just cut down the trees, but in some cases they re-sprout and we have to cut it again or graze it off. There may be a system to felling, and cutting the trees down like this can induce a fire risk, particularly in a dense plantation like this. So timing of year. This is stem injection. This is a very dense native forest regrowth area. Killing off individual stems to give the best stems some more time to respond, or ability to respond to the increasing light levels, is another technique. How you do the thinning, ring barking, stem injection, harvesting, whether you can sell those thinnings. Well, if you can find a market for small logs like this, well done. A lot of people are desperately looking for vineyard posts and pulpwood for. It's so hard to make it pay. These are very labor intensive. You've got to use a lot of equipment to move a lot of small volume material. I worry that a lot of forest growers expect to get a return from this thing. I don't. I just use some for firewood and let the rest rot. It's conservation value. It's biodiversity fuel, if you like, in the system. If you space the trees without pruning, you get large branches. So what we have to do is thin and prune at the same time. This is a small plantation of Sydney bluegum. We've gone through and we've identified the best trees and put tape around them, and we've pruned them up. And I'll show you how hard we prune. And then all the other trees are cut down. Now this is done in a number of steps. So in this particular patch, we've retained 4 or 5 trees and thinned the rest, and then over time we'll come back in 3 or 4 years, a couple of years time, and then thin again, and probably prune every year to try and get the result. Pruning is often called clearwood production because the idea is to remove the branch and then allow the tree to grow over that and produce wood without the knots in it. Now this is a real sample, so you can see I've cut the branch here and there's a little bit of rot traveling back down into the branch. You can see how the branch comes right back to where the pith, where the initial bud came from, and you can see how subsequent years' growth produced this clear timber, which is much more valuable and easier to dry. You can see as I dried this sample, it cracked along the pith of the branches as well as down the pith of the center of the tree. The orientation of the grain around the branches makes the drying very difficult, whereas this timber dries much more predictably. That's what we call the knotty core, the waste part of the tree in the center, and this is the clearwood zone on the outside. Now here's a sample of blackwood one of my students was working on. You can see how I cut and pruned the tree here, and we got subsequent growth of wood. initially sapwood, but over time that's converted to heartwood, and we're now actually milling some pruned blackwood off the farm as well. Where to cut? Some of you might have studied arboriculture. Really, we want to cut perpendicular to the branch. We want to avoid the swollen area. The way I look at it, you shouldn't be able to hang your hat on the tree, on the branch stub, because it should be close at the top, but it should be perpendicular to the branch so that you can actually allow that to grow. If a branch has a well-defined collar, such as this, we don't want to cut into that collar wood at all, because the collar is swelling is due to the fibers of the stem overlapping the fibers of the branch, and it's the fibers of the stem that bring the sugars down to help us heal over the wound. So this is where the cut is. Again, it should be circular because you're perpendicular to the branch, and it should be sloping at the top rather than sticking out like a little hat hook in some fashion. If you do that well, this is 1 year, 2nd year, 3rd year, you can see it heals over evenly from all sides because you haven't interrupted the flow of sugars down the stem. If you flush cut like this, you'll end up with an oval cut, a lot of bark damage. This is done with a chainsaw, and you won't get a good heal. This is a proper cut here. And you can see it's round, and it allows the sugars that come down the stem to feed all the callus material around that. So we get a good donut formation of healing over the top. Do not cut like that. So that's a simple guide to pruning. And how high to prune really depends on the species. If it's a high value fruit tree grown for both mango wood and mango fruit, you might only have 2.5 meters. Good blackwood, I've harvested logs that are only pruned to 2 meters, but our eucalypts we prune to 6 meters, and our redwoods we pruned way up here to 8 meters. This is me up 8 meters up a tree cutting branches off because it's a tall growing tree that guaranteed straight growth. It has a very high value timber and useful. So how do we guide pruning? How do I teach farmers how to prune? I get annoyed at some of those researchers who recommend pruning to a certain percentage of tree height, for example. It's like when I read that, I know that the people who wrote that have never actually pruned a tree, because when you're climbing a tree to prune it, you cannot tell how high the tree is. You cannot judge where 60% of the tree height is. It's these physiologists and researchers who don't have the practical experience to understand how you actually guide that management. And it's a great recommendation from a physiology perspective, but it's not lacks any practical sense. And if you prune all trees to the same height, that can be a negative as well, because some trees are going to be fatter than others and some are going to be thinner. And as a result of that, your pruning, even though it's to the same height, will have a very different effect on how much clear wood is formed around that stem. So we need a better way to guide pruning, one that we can use in a practical sense. This is a gauge, a horseshoe gauge I made out of plywood. It's got an 8 centimeter opening, and you put it on the tree where it fits, and I prune every branch up to that point. Now, if the forest the trees are uniform in their taper, this will be pruning to effectively a percentage of tree height. But this guide allows us to prune fat trees a little bit higher, skinny trees a little bit less, and it's all related to the subsequent wood formation on the stem. It disregards, in effect, the height of the tree, and it overcomes the concern about taper variability. So we go to a tree like this, put the gauge on, and then I prune it up to that point. It could be 8 centimeters, 10 centimeters, 12 centimeters, or 6 centimeters, or any measure, depending on how you think the impact of tree growth and the tools that you're using for the equipment. That will effectively, once it's healed over the wounds, give you about 12 centimeters in the center of the log, 12 to 15. That's not useful for timber production because it contains all those knots and the rot and the pith and all the other parts of the tree. Here we got, the farmers ask me, even when I show them the gauge, they say, how high do I prune? I said, well, just put the gauge on, you prune up to that particular point. You remove every branch to where the gauge fits. You prune fast growing trees every year because they grow so quickly in height, and then you go back and you prune a bit higher. Next year, you'll prune up to that point, and you stop when you reach the target height. Now, the target height could be a point where the tree becomes too difficult to prune because of its form changes. It could be because you've reached that limit of your pole or your ladder, or because you've actually reached a point where you guarantee that you'll get a log at the length you actually want off the stem. So using this technique, we call it variable lift pruning. You prune every tree up to say the diameter, such as 8 centimeters. So a fat tree is pruned, tall one is pruned a bit higher, a short skinny one is pruned to a much lower height, and it's variable. So it depends on how you're treating every tree as an individual, because when you harvest it, that is an individual log. You can't average out when you look about a forest. There is more pruning though. You might have noticed in an earlier photo, I had a gauge that had a second gauge in the back, and this is some gauges we made for teak farmers in Indonesia. The second gauge is there to be used above that height. Any branch such as this one up here, which is larger than that, we take it off now. We preempt the fact that that is a large branch, so in the subsequent year when we finally move the gauge up to there, this will be a very large branch. And this really comes from the practical side of work as well, because a large branch takes much longer to cut off, and it's much easier to cut it off when it's small. These other branches around it will compensate and use the available light, but this dominant branch will be removed, and that will help. So this is another example. This is a blackwood tree with a large branch coming out the side. The stem is only about 50 centimeters, so you wouldn't normally prune it just using the 8 centimeter gauge. 50 mils, I mean, the 8 centimeter gauge, but it's large, so we remove it. And you can see here, by removing that branch, we stop it growing any larger. And more importantly, we maintain a straight stem, because a branch this large can cause the main stem to head off in a different direction. Here's another large branch, larger than the gauge. The branch component of the gauge, take it off. This is one that I didn't do early enough, and you can see that's about 4 or 5 centimeters. Had I taken it off a year earlier, this main stem would be straighter. And I've lost some of my form because I've retained that large branch for too long. Double leaders are a real problem in some species. It's caused by the growing tip dying back. Could be due to tip moth in red cedar, or it could be frost damage or wind damage or insects. Two buds then take over, and those two buds are on opposite sides of the tree. It cannot suppress each other, and you end up with two stems with no sound link between them, and you can get splitting. These should be removed as soon as possible. They can be removed earlier than the 2 or 3 centimeters when you take off the large branches if they're obviously occurring, or at least take them off when they reach that 2 or 3 centimeters to prevent this subsequent splitting down the tree. So putting those two things together, I prune up to a set diameter, say 8 centimeters, or it could be 10, but let's just use 8 as an example. And then I look further up the tree and take any large branch off. The aim is to produce what I call a scaffold on which to grow clean wood on a straight stem. And by doing that, you can actually then subsequently get all that growth. So when combined with thinning, giving this canopy more space, we actually get rapid diameter growth around this core, and none of this wood will end up in your blackwood coffee table, but out here we'll have good, clean quality timber, as you can see around the pruned stems. If you prune but don't thin, you're pruning too many trees and you're not getting the advantage of the spacing. So you're going to be many more years before you get a return on that pruning investment. So here's looks a bit like Barack Obama with his young tree. He prunes it up to 8 centimeters and controls any large branches. Comes back a year later, prunes it up again. A year later, prunes it up again. Then over time, subsequently reaches the height that he wants, and then allows the trees to grow because he's thinned the competition around that stem, and he can grow it out to a large diameter, whatever required over time. And he can leave it there as long as he likes. If it's a healthy tree and gets larger in diameter, in most cases, you know, up to at least 1 meter, you can actually grow these trees out depending on what equipment you've got to do the harvesting of heavy, large diameter logs. Regular pruning leads to a more valuable log in those examples. Don't prune those form 3 trees. It's a waste of time. You can't prune a crooked tree to make it straight. You can correct some problems, but essentially you want a straight tree to get your return. I won't talk about gravitrophic and phototrophic growth. If you're interested in that, you'll pick it up. And it has an effect on which species we select and their growth rate in different characteristics. But these are the things I talk to farmers about. I was working in North Queensland. This is Agathis robusta, a species that will grow straight even if it's growing in the shade or light from one direction. That's what we call gravitrophic. It's ideal for use for timber production. Other species like redwoods do the same, and oaks to a lesser extent. They can give us much straighter trees. How you do the pruning? It really depends on your fitness, the equipment you've got, and other systems, whether you're prepared to climb a ladder. I've been up a bamboo ladder, and they're not very safe. I prefer to use a harness and a helmet. You can see my helmet. And I'll just show you a video of what I currently do.
Okay, we've got a larger Sydney blue gum here. It's got fairly large branches. It was pruned last year. You can see it is well over the 8 centimetre mark. So there's many branches I'll have to remove off this. I'll work from what I can from the ground. Cutting the branches off, not flush with the stem, just a little bit out so that they can heal over the collar. Find the right angle to put the ladder. With the harness, you put the harness on at ground level so that there's no chance of injury. Tying off as we go up. The vertical ladder doesn't have to be as strong as a conventional sort of painting ladder, so you can get much stronger fix with the tree. Makes a good work platform. 2 tools, the loppers you saw and the hand tool. For a branch that's in an awkward spot, better just to use your hand saw. Dead branches you pull off. Now I'm working up the stem. First find out where my 8 centimetre mark is. Every branch up to that point is removed. You can see how easy it is when you're on the harness to relax. Now as I look up, I want to make sure there's no branches over 2 centimetres in size. This one's definitely larger. And as is this other one. This one here. I need the saw for the next one. It's a large branch. Leave these ones because they're small branches. Large branches you should undercut first. And then over the top. Now it looks like that's done, except there's one more large branch. You can see here we have a large double leader almost. Not a perfect double leader, it's still sort of a branch, but it's competing with the main leader. So very keen to remove that one. I have to come in closer. And it's still got one large branch I just missed on the other side there. And because it's on the back side, it's very easy to take off with the saw towards you. So on this tree, we've gone up to the 8 centimetre mark, and I've taken off 1, 2, 3, and the four branches off. I've left smaller branches evenly around the canopy, and a good 4 or 5 metres of green crown still on that tree. By removing the leaf, I am slowing down the rate at which the tree grows in diameter down here, because the leaf produces the sugar, flows down the stem and grows diameter. But I don't think leaving that much canopy, I'm having any effect on height growth at all. Tree continues to grow tall. diameter is slowed down just for a period of pruning. But once I've reached my 6 metre mark, and this ladder is 3 metres to here, so I've still got a way to go next year, I'll have a tall prune tree with a straight stem, pretty straight, and Sydney blue gum, grow it out to about 80 centimetres in diameter, up to the first branch. Top of the tree can spread out. That's the factory that produces the sugars that run down the stem and grow diameter. So the pruning work is a little bit every year, but through that, probably 10 minutes per tree, I estimate, over its life. You can turn a tree that would otherwise be only good for firewood into potentially furniture grade clearwood timber. And that's the story.
So I've also got a little film here of using a tool that I have an electric pruner's secateurs, and these are unpruned redwoods on a neighbouring property, and I haven't got any like this on my farm because I prune everything. And these are my prune trees after 32 years. So you can see how I've pruned them up to 8 metres, and now they're put on the diameter growth because of the spacing, and that's the same size me. These trees are approaching 90 centimetres in diameter in 32 years. These are our younger redwoods. I use an electric pole pruner that allows me to reach up to about 5.5 metres. Then I use a small ladder and go a little bit higher with the pole pruners as well. I've sped this up a little bit, but they're electric pruners. You just press a button on the stem and that secateurs cut the branches. And because it's a geotrophic species, I said I wouldn't mention too much about that, the branches are very horizontal, so it's very easy to work from underneath and prune the branches off. And very rarely do you get a double leader. It does take a little bit more work, and the branches are easy to prune. If you prune on time and do that preemptive pruning of large branches, you shouldn't have any problems with a branch that's too large for the secateurs. Occasionally I have to mark a tree when I'm using this on the eucalypts and climb it and use a saw or loppers because the secateurs can't quite take them off. I'm taking off some epicormic shoots off the base of this one before I start working on it. Epicormic shoots arise after pruning because there's not enough canopy there to suppress the buds that are able to form in the stem. Same way as you have shoots coming out of a stem after a bushfire, redwood or eucalypt, you get the same thing after heavy pruning. What I find is that once the pruning's finished, a couple of years later, you don't get any more epicormic shoots, but they're easy to actually remove using the electric pruners anyway. It's a very neat system. It's nice and quiet. As I get older, I have to do less tree climbing, and you can generate a tree like that. So I talked about epicormic shoots. What time of year to prune? Well, there's lots of issues there, depending on species and climate to reduce rot, but also whether it fits into the farm work practices. And I like to say I prune in winter because I don't like tiger snakes too much. If you don't prune, that is an option, but you can use competition to control branches, but eventually you're going to get slower growth in that sense. So these areas here where the natural pruning of the lower branches has occurred, people get excited about this, but as soon as you space these trees out to get diameter at an early age, you're going to not get the self-pruning that you might want. Why do we start with more trees than we want to harvest? Because we want that mutual shelter, because in some cases, we need to suppress the undergrowth, particularly in the tropics. You want to be able to select the best trees, so your cull ratio will allow you to pick out the best trees. If there's variability, if you use clonal techniques, you may be able to reduce that. And you want flexibility in management options. You got to have spacing. You got to think about whether the trees grow away from each other. These are phototropic species like eucalypt will bend away from each other because they're crown shy due to the shading and rubbing between the buds. So you want a good spacing between the trees. So where to start? It really depends on where you want to end up. Having a clear idea of what your forest might look like in 10, 20 and 30 years time should govern the spacing and the arrangement of your initial planting and how you engage mixed species and other options. You don't have to plant at an even spacing. We've done a lot of group spacing where we plant 2 or 3 trees further apart, and then we just prune and select the best trees in this group. So we have our selection ratio, we have our spacing already defined, so the trees are nicely distanced apart, and we get the mutual shelter by planting them close together in some way. Tree establishment, we can talk about this when we look at case studies in more detail, but it's not a recipe approach. You've got to look at the site limitations and the purpose of the planting and what the goals are and who's going to do the management. And that's best. But ultimately, if you understand you can manipulate growth of the trees in a natural way, it doesn't require improved genetics, or it doesn't require fertilizer, irrigation, chemicals, or anything in order to direct the growth of those that natural growth pattern to generate a forest that looks quite different to be the one that if you just plant the trees and walk away. And I hope that provides some of the basis we'll talk about with Frank and Ben next week about how they're managing particular species for particular markets. That's it. Thank you. I hope you have time to watch it.